Hi, folks. We're going to go ahead and get started. Woohoo! Hello. All right. Thank you all for being here for our last seminar of this semester. It's been a really excellent semester of excellent speakers, and today is no exception. It's my honor to introduce our speaker, Vera Markgraf, Dr. Vera Markgraf, who received her PhD from the University of Bern in Switzerland and followed with a stint as a researcher at CNRS in France. I won't try and pronounce the institute in France because I would butcher it. But she came over to the US and was an assistant professor in the geosciences department at the University of Arizona for a number of years, and finally made her way to INSTAAR in 1981, where she spent 20 years as a research professor. In addition to this amazing career, many publications, much research, she's earned an honorary degree from the University of Bern and recently a Distinguished Career Award from the American Quaternary Association in 2019. She's now a retired research professor emeritus, and today we're going to be hearing about her work on paleoecological studies from the late Quaternary as they relate to climate change and interhemispheric linkages. So please welcome Dr. Vera Markgraf.
Thanks, Kathleen. Can you hear me? Okay. And thank you, Dr. Lewandowski, for inviting me for his anniversary celebration. I feel really honored to be here, and it is fantastic to see all these faces from 25 years ago. It was really a good time, and you'll hear all about the history. This is a talk about some science, but mostly about history. So my title build is from the Beagle channel. I think that fell off at the bottom. And I will begin with where I grew up. So the Alps, that was the panorama when I was growing up in Switzerland and southern Germany. And it was a panorama with some pretty crazy geology, big naps all over the place with glaciers that kept on receding year by year by year, ever faster from their 1880s 1880s trim line that you see here. That's the old trim line at 1880s. And can you imagine how big the glacier was at that time? And this is a picture from quite a few years back, so it's even further back in time. And a panorama with colorful alpine meadows. Every time, every season has this most wonderful floristic diversity and evidence of many generations of land use, even at the highest elevations. So for my dissertation, I was interested to get the long-term view of these different factors and their interaction, different features. And long-term meaning time going back to when Switzerland finally deglaciated 18,000 years ago. The picture you see, Switzerland was pretty completely covered by ice. And the red dot is the site that I decided to work on. It's a small alpine lake at the tree line and only about 20 kilometers away from the Matterhorn, but you can't see it. Anyway, this is the site, and the vegetation at the tree line is a diverse forest, and I cored several sediments out of this lake and analyzed them for their sediment composition and for the usual macro and micro fossils that are in there, including pollen and charcoal, and also algae to get a vegetation history, to get a lake level, lake situation history, and fire history. So after many months of sitting on a microscope, analyzing all the data, I finally plotted them up along a timeline. And so the left image shows you the timeline from today back to about 14,000 years. That's how long the record was. And the first thing when I plotted up the pollen data showed a major shift between arboreal and non-arboreal taxa, what I interpreted as an elevational shift of the alpine tree line, because I was sitting right at the tree line. So the moment you get more tree pollen, it means a tree line has moved higher up. So this is the curve that I reconstructed, and you can see that during the mid-Holocene, 7 to 5,000 years ago, the tree line was about 300 meters above the present, which in terms of summer temperature to what the tree line responds, the alpine tree line at least responds to summer temperature, means about 2 degrees Celsius warmer. And the most interesting thing, though, during this warm period was a replacement of fir by spruce. In this diverse forest up there with 4 or 5 other different species, that was the only thing that happened. And nobody had really worried about that before. So I looked at several records all throughout Switzerland, the lower panel here, and there the timeline is now from top to bottom, going back 18,000 years. And look at the arrows. The arrows are all over the place. All these records that go from west to east, and so northwest to southeast in Switzerland, the red is my own record. The arrow is all over the place. So it couldn't have been migration problems. And then when I looked at detail at the high elevation sites in the Central Alps of Switzerland, it showed that the highest sites were the first ones where this exchange happened, successively at lower elevations. And then I talked to some botanists and said, what's the difference between those two species? Fir versus spruce look pretty similar. And they said, oh, well, fir is very sensitive to disturbance, especially browsing. So I said, oh, maybe this is now the first time when human settlement began in that part of the Alps. And archaeologists knew that people had come in from the Mediterranean into the Central Alps. And at that time, mid-Holocene, warm period, all the passes were ice-free. So if you come with your livestock, where would you first go? You would stay where the nice meadows are and the beautiful grasslands. And successively, you would then go to lower elevations. You had to cut the forest because it was all primary forest. Now this, I thought it was a great idea, but it was very controversial. Yeah, if you just have a few data points, it's never enough to convince the scientific community that your idea would go anywhere. So at that time, I was ready for other challenges. And I had moved to a French research institute, Centre de Faible Radioactivité near Paris, which was mostly working on isotopic research, but not just for paleoclimate, for many different isotopic projects. And so for that reason, it was co-funded by the French Atomic Energy Commission. And they had a great agreement with Argentina, with the Argentine Atomic Energy Commission, a cooperative scientific agreement. So I heard about that and I thought, well, what a great idea. Go and check the paleo-environmental potential of Argentina, specifically Patagonia. So I packed my coring gear and a recommendation letter to the big bosses there, asking for logistic help, and I got it. They, for about 6 weeks, we traveled from latitude 38 to 50 south and cored several sites along the foothills of the Andes. And it turned out those were the first record going back to deglaciation times for southern South America anyway. But if you think about Patagonia, you probably imagine just large steppe areas, isolated, lonely, windswept grasslands, heathlands. But the term Patagonia itself includes the Andes and the lowlands to the west of it in Chile. And those are heavily forested with the most beautiful, most diverse kind of forests, typically Southern Hemisphere taxa, all uniquely Southern Hemisphere. So I have a few pictures. When you come in from the north, from the equatorial latitudes at 38 is where the forest more or less begins. You have this deciduous and evergreen mixed forest with some conifers you probably know from the botanical gardens. The monkey puzzle tree, Araucaria araucana, and Alurse, cupressoides. And just recently, the endochronological work had dated one of the still living specimens of Alurse, the bisabuelo, the great-grandfather, to be 5,680 years old. I think that's what it says, yeah. 5,680 years old. That's pretty remarkable because it's about 1,000 years older than our oldest bristlecone. So it's the oldest conifer globally. Anyway, so when you go further south, now polewards to the mid latitudes, you get into did I do that? I hope not. You get into rainforest area, like this area here. In the deep valleys, the Andes have a very high topography. And to the west of it, you get into really dense forest. Well, something is missing there, but that's okay. One picture I can see, but it's not let me see. There we go. And you get into really dense forest, evergreen at the lower elevation, deciduous at the upper elevation, with bamboo as an undergrowth. So if you go off the trail for about 2 minutes, you don't know your way back. It's very, very dense forest. And then on the Chilean side, then the lowlands, you have typical temperate rainforests with an undergrowth of ferns and mosses. I mean, very dense forest there. And once you get even further, there you have the two rainforest types. And then when you get further south, now latitude 50, 52, 55, you get into vast areas of moorland that you can never really, no, go back, that you cannot get to until you rent a boat. And we did that in 1995. And I don't know if you can recognize some of the people on it. There's my last student, Uli Huber, and the two postdocs, Mel Reisner, Bruce, you'll know those guys, and Ray Kenny, and Platt Bradbury, and the captain. So I did some marine work then, and as well, trying not to get seasick. And so now the reason for this great diversity of forest types along the latitudinal range has to do with the amount of precipitation it gets. So the southern westerly storm tracks are shifting poleward in summer and equatorwards in winter. And the result of it is that you have at the low latitudes about 2,000 millimeters of precipitation to increase to over 6,000 millimeters. That's 6 meters of precipitation per year. And once you get across the Andes, the rain shadow is so steep that you fall down to about 400 to 600 millimeters. So it can be a very rainy field work, or it can be a very dry field work, depending on which side of the Andes you are. So as I said before, the vegetation is uniquely Southern Hemisphere. So the first thing, before I could analyze the records, I had to learn the vegetation. And here you have just two pictures and their respective pollen types. So one is the southern beech, which is one of the most common tree taxa, very different species, evergreen and deciduous. And the other one is winter spark, Trimis winteri, with its very unique pollen type. And it was known, winter spark has been famous for the early explorers because its bark is very high in vitamin C. And so that could prevent scurvy at the early explorer time. Anyway, after I learned the pollen types and vegetation, I came to the University of Arizona and I started to involve graduate students, as I did at INSTAAR then as well. And it was, the idea is to extend the network. I mean, you need, if you work between 38 and 50 degrees latitude, actually 55 at the end, you need a lot of records in between to get some idea of what really the environmental changes are. So you can see a piece of core there. with a Livingston core. Mostly it was hand coring, sometimes with big tripods when you had 10, 15 meters of sediment hauling up by hand. That gets pretty heavy. Anyway, so these cores then were analyzed the usual way, paleoecological techniques, pollen and charcoal. And I'm showing you one pollen diagram. And on the y-axis is time from 0 to 18,000 years ago. On the x-axis, then you have charcoal at first, the black records, charcoal amounts. Yellow are the non-arboreal types, grasses, herbs, other Peace taxa, and in green, the tree. So this is how a pollen record looked like, and having a series of those records all up and down the Andes, then you can start getting up with a general picture of what really happened at the time. And at the right side, you see a picture of how far the glaciers during the ice ages extended out into the steppe area. It's a pretty unique picture from a military airplane that we had to use because no other airlines were going where we wanted to go. So then when you have enough records, you can start mapping environmental conditions in time slices. So this is a time slice for Southern South America and New Zealand. And I wanted to see what the vegetation looked like at the beginning of deglaciation. So as you can see, the forest was shifted way towards the northernmost end of where it is today in South America, as well as in New Zealand, because in both areas, it is the westerly storm tracks that provide the necessary precipitation for those forests to exist. So as you can see in the climate picture, the storm tracks were shifted equatorwards quite dramatically in relation to the much steeper pole equator temperature gradient, which in turn was related to much more extensive Antarctic sea ice. So this is one of the time slices, and you can do that for all the different periods and see how they compare across the Pacific, because ultimately New Zealand and South America have a lot in common, not just the vegetation. So all the records we had so far from Southern South America were not older than just the beginning of deglaciation. So then we decided one day we want to see if there isn't any way to get older records. Well, the only older records you could possibly get are from this few large lakes out in the steppe area. And now this is a very different kind of research. Suddenly you are doing logistically things way beyond my own experience. So I got together with Kerry Kells, late Kerry Kells in Minnesota. He had worked in Switzerland before, and originally he came from the marine system. And so he had started to develop a lake core system for the Swiss lakes. And then together we developed this Cardiel project. And I should have shown also the picture how 90% of the time the winds are so strong that you could not get onto the lake. And you just have to find a window where it was as calm as it shows up here. So NSF allowed me to build this coring platform, and which is still somewhere down there being shipped from one lake to the other. I don't know if it still works, but it was constructed by some salmon hatchery fences that they had left over on the shore and brought in by truck 500 kilometers inland to this site. And so first we had to do seismic to know where to core. And you see there are some dramatic differences in the thickness of the sediments throughout the lake. The lake is about 20 kilometers across and 76 meters at the deepest part. So it's not a terribly deep lake, but deep enough for being scary. And it has fortunately quite a few different ashes that you can use as time markers that had been dated on land. And to the great surprise about halfway down that core, it's a 12-meter long core that we got out with a Kohlenberg coring equipment, the lake had completely dried out. So, I mean, talking about a big lake suddenly being dry, initially the oldest part of the sediment is a shallow lake that we know from some of the plant data, and then it totally dried out, and 13,000 years ago. And by 9,000 years ago, it was 50 meters above the present. So, I mean, it's a big lake out there that seems to be a rain gauge that is just amazing. And it's hard to know. We still don't know. I don't think there was ever conclusive argument shown. The precipitation could not have come from the west, from the Pacific. It had to come from the east for being an early Holocene high lake level that way. And climatologists have a hard time to see that, how you get so much precipitation from the east. Anyway, I had to show you this picture to show you that I got into some pretty heavy duty stuff too. But unfortunately, because the lake is this big, on the deep core, there were no preservation of pollen. The only indicator, proxy indicator, were ostracods. And we have quite a good record on ostracods and stable isotopes on the ostracods. But pollen were not preserved. So our record from this lake, the pollen record, is only from a nearshore core we can get. Anyway, so much for my own research in Patagonia. But when I moved to INSTAAR, suddenly there were some new opportunities for collaboration beyond Patagonia. And the first one, with NOAA building being close to us, was together with Henry Diaz, a climatologist from NOAA, who just at the time worked with John Andrews. And when I met him, he told me that his main interest was really El Nino southern oscillation, and especially the effects of the two extreme ends of El Nino, of ENSO, El Nino and La Nina, onto precipitation and temperature patterns in the Americas. So at the time, there was quite a concern that those extreme members of ENSO could become more common with global warming. And he was thinking that we should get together and look at paleoclimate records and see if there isn't any analog time that would have shown these extremes. So we convened a meeting here at INSTAAR in the old building and brought together climatologists and oceanographers and scientists that had interpreted their proxy records in terms of El Nino patterns or El Nino variability. So those were as well high resolution records like tree rings or archival records or even marine records, or lower resolution ones just like pollen records. And it was probably the first time these two groups sat together. There was a lot of give and take. You cannot interpret it this way. Climate doesn't do this way. And it was getting sometimes pretty heated, but the chapters that emerged from this meeting were worth publishing, we decided. And so this was the first book that I think was a comprehensive issue for all the present day and paleoclimate El Nino data. And about 8 years later, a lot has changed. The name had become a household term. There was much more information on multiple decadal El Nino patterns that then were excited for us that had not the high annual resolution proxy data to use. So that was the second edition that we published then in 2000. Well, another collaboration that was very exciting was with Jim White when he joined INSTAAR. So I approached him one day and telling him about this peat core I had with very well preserved mosses and sedges. And if it wouldn't be possible to get some quantitative climate record out of that using stable isotopes. So my main interest was in deuterium, hydrogen isotopes, stable isotopes. And, and he agreed, but he also wanted to do the carbon isotopes for CO2 reconstructions. So the reason why that was possible is because mosses do not have stomates. Stomates regulate the uptake of water or of atmospheric gases. So mosses just take up whatever is there. Sedges, on the other hand, have stomates, and they will regulate the water, and they can give you information on water changes, hydrologic changes. So we had collected modern mosses all along the latitudinal gradient and analyzed for the hydrogen ratios, the deuterium ratios in the modern mosses and their relation to the meteoric water temperature. And the cellulose of those mosses were beautifully corresponding to the respective water temperature at every site. So we felt very good about it and going and analyzing the deuterium ratios in the fossil mosses. And you see a picture there on top. Those are mosses and sedges. And this is the record that we got. So here you see the deuterium curve. And it begins 16,000 years ago to 11. I just depicted the late glacial interval. And so from one end of the curve to the other extreme, it's about 10 degrees Celsius difference. So it's a pretty dramatic temperature change that you have during the late glacial, going back and forth between warmer and cooler climates, cooler conditions. And so the nice thing about it is that the pollen record done at the same levels actually had a good, compared really well with the temperature curve. And at the very base, you see the first increase, temperature increase, and tree pollen as well as heath pollen are corresponding to this temperature increase. And when it got cooler again, you have instead more grasses expanding. And the most exciting thing for me was actually the interval YD, the Younger Dryas interval, because for a long time when I had those records, I saw that there were charcoal. It means there were fires during the time that in the Northern Hemisphere interval, Younger Dryas interval, was considered cold and dry. And I always maintained you cannot have fires under cold and dry conditions. You have to have warmer conditions, and also the vegetation showed the warmer conditions. So it was very nice to see that actually the delta D confirmed my interpretation from before. Well, now for Jim's interest in the it doesn't want to go down. Chad, slide. It's stuck. I don't know why. I can see it, but it's stuck there. There we go. Anyway, so this is, I'm glad Chad is still here, my favorite person. From way back when, my favorite church. Anyway, so the C13 data, then the same thing. If you, because mosses don't regulate the uptake of whatever is in the environment, and if you can take off the moisture changes by using the data, the C13 from the sedges, you actually can reconstruct the central panel, you can reconstruct the CO2 concentration. So the curve, the continuous curve is our data, and then the dots are the Antarctic ice core, bird ice core data. And it shows a pretty good correlation between what we found at a much higher resolution than the ice core in terms of variability of CO2 changes in the past. So it was a complete experimental new approach, and don't think anybody has ever been able to repeat this one, just because you don't have peat cores with the same high resolution and or preservation of mosses and sedges. And then the last panel, we superposed the delta D data with the CO2 concentration. And at the very beginning, 16,000 years ago, it very clearly shows that temperature increased before you get the CO2 increase. Now, I think that's known by now from many other records, but it was fun to see that coming from a peat record out of all places. Anyway, this was a fantastic collaboration possible because in INSTAAR you run across people and you ask them a dumb question and they are sometimes willing to listen and write a proposal with you and you go from there. And maybe because of the INSTAAR's international atmosphere, one day I came up with this crazy idea to start collaboration along a pole, equator, pole, paleoclimate of the Americas transect called by Zimi coined the term PEP. So I had several regional meetings in INSTAAR one for North America, in Mexico for the central part, and in Mendoza in Argentina for the southern part, to get people excited about thinking beyond their own data and beyond national boundaries especially, and start talking to and exchanging data and think about linkages. And the time was ripe. In 1998, we had a meeting in Merida in Venezuela, and in the middle panel, you can see one of the approaches that was used in order to get an idea about the linkages. And so what this shows is essentially water balance interpreted from all kinds of different proxies from lake records. And so the horizontal curve, the horizontal line is going from 18,000 to today. And the red dot is just 10,000 years ago to give you a time frame. And so it shows in those vertical bars the water balance from lakes from Alaska all the way to southern Patagonia. And even not knowing any detail, you can see quite dramatic differences along this transect that give you an idea how the linkages are between the two hemispheres. So it was an exciting meeting. We had data from, as you can see, instrumental data first, then last 2,000 years, naturally ENSO had to be part of it. And then the human dimension of climate change as well, which was quite interesting because it did show, especially for Central America, where there are a lot of records, how relevant climate change is for societies. How the more developed a society is, the more difficult they can deal with climate change problems. So it was a fantastic meeting. And we were very lucky. It spawned several other such interhemispheric transect, Asia, Australia, Europe, and Africa. And they all had the same kind of exciting meetings, bringing together global community under the PAGES umbrella, Past Global Change, one of the programs with the International Biosphere Program. So it was a very exciting time, I think, meeting people from all different disciplines and different countries, trying to figure out global change in this way. Okay, so this is the story of my academic life, and it shows the role that chance and the academic environment played in order to make your career. Thank you.
That was a great talk. Thank you. Um, so I was curious about the lake that dried up. What was key evidence that you saw there? And also, was that kind of an inflection point, like in terms of plant and animal communities? Did they all come back after, or was there a big shift? Oh, yeah.
It's nice you brought that up because despite the fact that there was much ice cover over the Andes into the lowlands, the topography of the Andes is such that there were lots of places of refugia all along the transect. So whenever climate change, um, they came right back locally, regionally. There was no migration problem in the southern hemisphere, not even in New Zealand either. So I think it has to do with the topography. The mountains are right near the coast. So you always have some moisture coming in. It was not completely total desert. And then you had the steep valleys that were enough protection for those forests to survive. And genetic data actually showed that very clearly. There was some pretty good regional differentiation in some of the trees species that they looked at, different for different latitudes. Does that answer your question? Yeah.
Oh, wonderful. Wonderful talk. So it doesn't matter. Where would you think the future is for paleontology? I've heard many people think it's either a dying or it's a brand new thing. And I think you might have a really good idea, especially from your work with the Pages community. Where do you think the future of paleoclimatology is going?
Well, one thing I have to say, I'm a field person, and I'm afraid that is kind of a field that has fallen by the wayside. People are not too excited about working in a field anymore. And it started already at my time. It's hard work, be out there and camping and getting wet and dirty and all the other things. And so I feel that is one of the reasons that paleontology, that our field is no longer getting new input. If you're not out of the field getting new records, you don't have the data then to take the next step and do computer modeling or ecological modeling. It dies out after a while. And so I don't know what to say. It's still, I still feel for myself, field work is exciting. That's when you see things and when you get these ideas about what may have happened and what may happen in the future. But computers don't tell you that because computers are stuck with what you have. So now I know it's not a good answer to your question, really, but I don't know where the future is taking us. I mean, I'm not. Maybe I will make our records. We don't need to do the work anymore. Maybe you'll just make us pollen records from all over the world, and we don't even have to worry about getting them, analyzing them. So that's what I would say.
Thank you so much for your overview of your career. It's fascinating. Um, I was wondering whether you could give us an overview of what is expected in the near future or in the next couple centuries, especially in the southernmost tip of South America, and in terms of the interhemispheric connections. And what are the main changes that you're anticipating happening deep south there, and especially, I don't know, I would imagine that the southern westerlies will be potentially shifting further south.
What's the future? um, well, I mean, over the time I've been working there 30 years, 35 years, definitely Patagonia in general has become much drier. I think overall the westerlies are much shifted to a lower latitude in general. But I think we need to talk to the oceanographers and climatologists about that. In my own, another big problem is the human impact there. I mean, ultimately in the Andes, big fires have become very prevalent. I mean, destroying much of the forested areas all along the Andes. And that again produces another climate change. It makes everything drier. Once you have no more forest left, you have less snow in the snow fields. The Patagonian ice field itself is not a cold ice field. It's actually a warm-based ice field. I mean, I think the future looks very dire for water sources. I mean, you hear about it more from Ecuador and Peru, where they are totally dependent on it. But it's the same thing in the higher latitudes. A big question is still ENSO. You know, what will happen to ENSO? Will it really become an El Nino pattern for good and be stuck? I mean, we're getting into El Nino right now, so you'll foresee what will happen in this neck of the woods about El Nino. So I don't know. I don't think I can answer that very clearly. I mean, it's a very complex issue. I mean, you have all these different forcings. I mean, along the latitudinal transect, that was the main conclusion, that at certain times, one forcing overpowers the other. It was clear that we did not have El Nino patterns prior to 5,000 years ago in southern South America. So they only appeared after 5,000 years ago, as you can tell. So, you know, you have these changes in forcing through time. And what would the future do with more global warming? I think that it's anybody's guess at this stage. Sorry.
Thanks, Vera. That was a wonderful talk. You talked about seeing in your records in the Alps that there was evidence of perhaps human impact on the vegetation records you were looking at. There are people in the Andes and in South America as well. So do you see a human imprint on the vegetation records you looked at there?
Yes, it's in the southern part that was mostly my talk about. The impact is quite recent. Europeans came in the 16th century from the coast, and actually primarily in the high latitudes initially. And but they were sheep herders, and there was not much destruction really of the environment with the sheep herders. It only became an issue in the late 19th century, really. And that's what the devastation, one of the pictures I showed, the coring picture, the whole forest was cut down of a vast area because they came with cattle, you know, and sheep were no longer economically useful, so they brought in cattle, so they needed more land. And so that devastation is obvious. And as well as in Chile as in Argentina on both sides. And then, as I said, the fires have come in addition. And so, I mean, the human impact, the earlier human impact until 1600s, 16th century, was hunter-gatherer. I mean, there were all these bands that showed to appear 13,000 years ago. I mean, the record is quite long for humans arriving even in Tierra del Fuego 13,000 years ago. But it was hunter-gatherer, very small groups apparently, and they may have set fires at some stage, but that would have been pretty much small scale, not this big scales you see today.
So it's the cows.
Thanks so much, Vera, for that perspective. You have strong connections both with the European science community and across the Americas. And a lot of the PAGES activities and the PEP transects were really exciting times. my sense now is that the Europeans are still pretty active at bringing things together, but I don't see the America-European connections as strong. Do you have a sense of if that's correct and why that might be?
Well, I think the Americans have always been a little hesitant about pages. And it started from the very beginning because the question was to support the pages office, where's the money coming from? It takes away from my grants, right? And it was Herm Zimmermann, who was really very strong for a while behind pages that made sure it's a co-funding from the Swiss Academy of Science and NSF pages, the pages program. And and so what I've been seeing in the last 15, 20 years is that it's more oriented to topics. So when you look at the newsletters, which I think are fantastic still, if you get them, it's much more topic oriented. It's much less global anymore. I think there comes a time for these things. You know, the global time was with the PEPs essentially. And now it's much more linked to the last 2000 years or water changes in glacial extent, or I mean, you look at the newsletter, it's much more topic oriented. And so then it depends who wants to collaborate. Yeah, I think it's always been a little bit of an issue. You want to be spending money on an office versus on research. But I still think they are very important for their activity with younger science from the third world. I think that's one of the big issues. They always have money for people coming in from Africa, Asia, whatever, to collaborate. So I think there's a place for those things. And you may say the same things for AGBP. What's the place for AGBP nowadays when people don't believe, when one of the big countries doesn't believe in global change anymore?
Vera, thank you for that wonderful talk. You said that when you first started working on El Nino, that part of the idea was to see how the pattern might change with global warming. And maybe you just answered this question really, but do you see from that early work, and that being the premise or one of the premises for that work, have you seen a change with global warming? Yeah. Okay. Okay. Yeah, thank you. I have that book, by the way. I'm so happy.
I know it wasn't important.
I think so. That's all the questions. Let's go ahead and thank our speaker, Vera Markgraf, one more time. And I'd also love to give a thank you to Joe and Chad and all of the folks who have made these seminars go off without a hitch. They've gotten us pizza every time. It's been wonderful. So give them also a big thank you.